All right, so I'm going to skip to this slide here, which is from your book on page 30, figure 215. This is a drawing of how some of the experiments are done where we detect the sensitivity of light of rods versus cones. Now remember, cones are centralized on the fovea, which in this picture here is indicated. Here's a cutaway section of the eye, right? So let me orient you. So this eye's looking in this direction. Here's the cornea. Here's the lens. There's the pupil, right? So the light is traveling towards this eye, gets focused by the cornea and the lens, and then gets projected onto the retina. In this picture, here's the retina. This little yellowish strip here is the retina. The fovea is right here. And remember, that's where most all the cones in your eye are located. So if I want to see, if I want to test the sensitivity of light of the cones, all I have to do is light adapt somebody. So have them sit in a light room for about 30 minutes, and then put them in a completely dark room for another 30 minutes, and then have them look directly at a spot directly in the front, and then turn a knob. And whenever they're able to perceive the light that they're looking directly at, that will give me the threshold for the sensitivity of that part of their eye, which is made up only of cones, right? Now, but what if I wanted to test the sensitivity of the rods in that same person? Well, what I would do is have them look straight ahead, but instead of having the light there straight ahead, which would project it onto the fovea, which is full of cones, I have the light off to the side. So I have them look here, but when they're sitting in the dark, I have them look at this fixation point straight ahead, but then I have them turn a knob. And then they tell me when they're able to detect the presence of the light. Okay? What you're going to find is whenever you move the light off to the side from the fixation point, they're able to the threshold for detecting the light is much lower. In other words, the rods are much more sensitive to light. Once you've adapted to the dark, the rods are more sensitive to light than the cones. So it doesn't take much turns of the dial for a person to be able to detect a little light appearing here off to the side, whereas it takes a few more turns of the dial for them to detect the light if it's here in the middle, because here in the middle, all we're focusing on is cones, and cones aren't as sensitive to light as the rods are because we use the rods for night vision. We use our rods to see in the dark, whereas we use our cones to see in the light. Okay. I'm going to show you this picture here. This is probably, it's better to talk about this picture because this is a classic picture, right? You really need to know this picture because it's a classic shot, or it's classic data on dark adaptation. In other words, how your vision adapts to, the dark, okay? We have three separate curves here. We have one curve that tells us what our sensitivity to light is as a whole, just with our eyes, with both rods and cones working. And then we have one curve for the rods and one curve for the cones. And this is so that to illustrate to you the different role that the rods and cones play in allowing you to be more and more sensitive to light, or to adapt to the dark and adapt to the light. Let's look first at the red line. Okay, this is your vision with both rods and cones firing away. Okay, and this is what normally happens to you, right? And let me orient you to this graph first. So along the x-axis here, we have time going from 0 minutes all the way to looks like about 40 minutes, right? Time. And then along this axis here, we have sensitivity. Now, the weird thing about this graph is that the y-axis here is upside down. So you would think that this would be high sensitivity and this would be low sensitivity, but it's flipped, right? This is high sensitivity here at the bottom and low sensitivity at the top. So low sensitivity means it takes a lot of light before you can perceive it. High sensitivity means you're able to perceive very small amounts of light. You're highly sensitive to the light, so you can perceive very small amounts of it. Okay, so that's what that means. So let's take a look at the red line, which kind of goes here, kind of does this little curve, and then it has this little break where it kind of just takes a while. After about 30 minutes, it goes down to about here. This is a chart of your light sensitivity as you adapt to the dark. Okay, so think about it. Think about the times that you've been like in a bright room or in the bright light, and then you go into a completely dark room quickly. You switch from one to the other very quickly, like going from the parking lot of the movie theater to the movie theater, right? If you notice, it takes you a while for your eyes to adapt to the dark. In other words, you're not able to see very well when you first enter that dark room, right? It takes a while. And that's exactly what this red line is indicating. As soon as you go into the dark, you start becoming more and more sensitive to light. Then, at some point, it breaks here. Whoops. Oh, God damn it. I did it again. Sorry about that. Oh, let me, this mouse is a little too sensitive. Okay. And then at this point here, the break continues, right? So you get a little bit less sensitive, and then here, the break continues, and you get more and more sensitive to light until after about 30 minutes, which is about this mark here, after about 30 minutes, you can see as good as you're going to be able to see with whatever light you have, right? This curve here describes our adaptation to the dark, okay? How our eyes become more and more sensitive to light the longer we spend in the dark, okay? Now, this curve has this goofy shape, this little break here, because it's a combined action, or it's the combined effects of the rods and the cones, okay? Um, as soon as you go into the dark, right, your rods begin getting they're not being washed out by the light anymore. You're in the dark now. So the rods start coming online, and they get more and more and more sensitive to light. They start working better and better and better until after about 30 minutes they're firing away, okay? Now, remember, rods are specialized for nighttime viewing, for viewing in the dark. So this is their job, is to get more sensitive as you get into a dark area so that you can see better. But it takes about 30 minutes. It takes about 30 minutes for your rods to come online and start being sensitive to whatever light is present. Your cones, on the other hand, they start increasing in sensitivity too. But you have to remember, cones are designed only for light vision, for vision in light. So they can only become so sensitive. After a while, they stop, and then they just shut down, and they're just sitting there. They're as sensitive as they can be, but they're not going to function very well because they can't get any more sensitive. That's as sensitive as they can get, right? So as you stay longer in the dark, your vision is slowly being control or taken over, control mediated by the rods, because the cones are no longer able to function. There's not enough light for them to function. Now here's the funny thing, right? This break right here. I don't know if you remember, but if you remember taking your driver's ed class back in high school, when is the most dangerous time to drive during the day? In the 24-hour day, when is it most dangerous to drive? It turns out the most dangerous time to drive is dusk, right at the time from when the sun is up to the sun is set. Okay, right after the sun sets, right? Right after the sun sets is dusk, and that's when it's getting darker and the sun is going down, and there's less light. The reason it's so dangerous to drive at that time of night is because you're here. There's too much light for the rods to be functioning. So the rods are like out about here somewhere, right? There's too much light for the rods to be functioning, but there's not enough light for the cones to function, right? They're starting to shut down, right? They're starting, they're as sensitive as they're going to be able to get, right? So when dusk rolls around, you're to like here somewhere, right? With insensitivity, right? Um, because your cones are shutting down. There's not enough light for them to work, and your rods are there's still too much light out there at dusk for them to all to come online. It hasn't gotten completely dark yet. So dusk is a really dangerous time for humans to be moving around because our visual acuity is not that good because our rods and our cones are not online yet. The cones are still are shut down because there's not enough light, and the rods have not come online yet because there's still too much light out there at dusk for them to be fully able to go all the way down and adapt to the dark. Okay. Um, let's see. Okay, so when we're looking at the dark adaptation curve, as I said, you can test cone adaptation, right, by simply focusing the light on only the cones, right, and not on the rods that are outside. So only focus it on the fovea, right, which is where all the cones live. Um, once it's dark, right? Once it's dark, once you get into the dark, your cones start adapting to the dark, but they only do it for about 3 or 4 minutes, and then after that, they're like, "Well, I'm a cone. I've adapted to the dark as much as I can. I can't. This is it, right? So it's only 3 or 4 minutes that they adapt. The rods, there are certain people out there that don't have cones. Believe it or not, they don't have cones. They're born without cones. They're called rod monochromats. So they see everything in shades of blue and gray, and their vision is terrible. They have very terrible vision. But these people do exist, and when we use these people who have only rods, we show that the sensitivity takes about 25 minutes. It takes about 25 minutes for the rods to adapt to darkness and come online. Visual pigments. Remember, the visual pigments are these proteins that live in the rods and cones, and these visual pigments are the molecules that, when they get hit by a photon, they change shape, and that causes a cascade of events, which leads to a neural firing. So the molecule changes shape. Once the molecule changes shape, the opsin and the retinol separate from each other. They break apart. Okay? And that process where you have lots and lots of opsin and retinol molecules broken apart is called retinal bleaching, right? And that's where you have a lot of retinol and a lot of opsin that's separated because you've been using your eye a lot. You've been looking at a lot of light. There's a process by where the retinol and the opsin are recombined so that they can be sensitive to light again, right? And it takes a pigment after it's done the separation, after it's hit a bit of light and changed its shape and broken away, after the retinol opsin have broken away, it takes the cone pigments about 6 minutes to regenerate that molecule, to hook the molecules back up together. Rod pigments take over 30 minutes to regenerate. Remember, rods are specialized for the dark, so there's not as much light out there. So you're not losing as many molecules in the dark as you are in the daytime. So there's not a need to replace those rod pigments so quickly. So it takes about 30 minutes to regenerate the retinol opsin combination. Uh, Whereas in the cones it takes about 6 minutes for your eyes for the cells in your retina to regenerate that. But we're going through a constant process as we're seeing. We go through a constant process of using a molecule, breaking it, it breaks apart, and then it gets snapped back together again. There's this constant cycle going on. So there's always molecules being recombined, always molecules that are absorbing light and breaking apart. and always molecules that are being reconstituted, put back together. That's some of the activity that's going on in your retina while you're seeing, right? So here's a cartoon drawing. You can see why it's called retinal bleaching because this is a retina. This is actually a dissected retina. It's been taken out of an eye, probably a cow eye, perhaps. But this is what it looks like when the retinol and the opsin are linked together. And this is what this this is what it looks like when the retinol has been activated by a photon, right? So it gets a little bit lighter. And then after it changes shape and gets activated by the photon, it breaks. It breaks away. The retinol breaks away from the opsin, and you end up with, if you look at a whole bunch of retinol and opsin, which millions or billions of those molecules are in this tissue here, billions of these molecules are in this tissue here, you'll see that they're bleached. They've changed. They no longer have this reddish tint. They have a more light tint to them. Okay. Now, if this retina was attached to a living organism, the animal would still be alive, and what you'd have here is this process where you would have enzymes that would go through and grab this guy and link them back together again. So you would you would always have a nice fresh supply of the retinol opsin combination, so you can see.